Climate change is a hot topic. In Canada, emissions from landfills account for 20% of national greenhouse gas emissions. A portion of this contribution is attributed to fugitive methane gas emissions, a gas that is 36 times more potent than carbon dioxide over a 100-year period. The take-home message of this presentation is that help is underway to reduce fugitive residual emissions from closed landfills where gas collection is not effective or no longer viable. My name is Bria Nelson, and in this presentation, I'll show you how. Gas collection systems involve wells beneath the surface that vacuum landfill gas out for treatment and utilization. Electric power generation is a successful and widely used gas-to-energy process for methane recovery. However, when landfills close, methane is still produced for up to 100 years. The concern that arises in this case is that the methane concentrations eventually reach a value that is too low for energy recovery or flaring, but may still threaten the health of nearby residents and harm the environment. A solution for this problem has been desired for decades, but now, with COVID baby diapers amplifying landfill volumes globally, a solution is critical. Passive methane oxidation biosystems, or PMOBs, have been investigated for the past 3 decades. PMOBs house methanotrophic bacteria, or bugs, which oxidize methane into carbon dioxide. These systems can be implemented at the surface of landfills and naturally filter the methane out of landfill gas. This concept is proven to work. It has been tested in several landfill applications globally, and under optimal conditions, it's achieved 99.9% efficiency at the removal of methane. However, these studies have yet to develop a clear design criteria. The main goal of this study was to design a PMOB following newly developed criteria, then construct and test it. A PMOB implemented at the Kitchener landfill will operate under uncontrolled conditions with challenges like rain, snow, changes in temperature, and barometric pressure fluctuations. Testing a design procedure to implement this low-maintenance technology will have a significant impact. This is our goal. As I mentioned previously, a lot of studies over the past few decades have dealt with the environmental and biological considerations of PMOBs. It's the hydraulic behavior of these systems that is yet to be well defined. The originality of this study lies in the monitoring and evaluation of the hydraulic behavior in these systems and the ability to apply them in cold climates. The study aims to develop a design procedure which considers the parameters previously defined with a deeper understanding of the hydraulic behavior, and a methodology to produce and maintain heat through Canadian winters. This information will optimize the effectiveness of PMOBs in fugitive methane mitigation applications. A pilot-scale PMOB was designed and constructed here at the closed Kitchener landfill in southwestern Ontario. The landfill has been closed for over 40 years and has struggled with methane mitigation, specifically localized areas of fugitive methane emissions. These are called hotspots, where methane gas escapes the collection system. PMOBs consist of 2 main layers: the lower gas distribution layer, or GDL, where biogas enters the system and is distributed throughout the surface of the PMOB. Above the GDL lies the methane oxidation layer, or MOL, which serves as a house for the bugs. This is where the methane gas is oxidized. The design phase involved lab tests to help determine what material was best suited as the MOL. The house must maintain specific conditions in order for the bugs to thrive. The criteria were based upon material characteristics as well as availability of the material. A compost material mixed with recycled plastic pellets was selected as the MOL since it fit the desired characteristics and the landfill has availability in surplus. Many factors were designed and implemented in order to obtain optimal living conditions for the bugs. The structure was designed to ensure sufficient drainage of seepage in the PMOB. A heat trace wire is integrated in the system to provide optimal temperatures for the bugs, and an air inlet is incorporated to provide a sufficient supply of oxygen. The PMOB is contained in a wooden box structure. A foam insulation layer was placed to help maintain the warm temperature inside. a geomembrane liner was installed to seal the system, preventing outside air from entering and forcing seepage to drain out of the system in a controlled way. The PMOB is set on an 8% slope to allow excess moisture to be drained out from a downslope drain. The importance of this design lies in the cruciality of avoiding a PMOB fully clogged with water, thereby preventing upward migration of gas at a sufficient rate. In other words, we want to avoid clogging the pore voids with water. The geomembrane is followed by a geotextile layer to protect the membrane from punctures that would come from the GDL. Inside the gravel that makes up the GDL lies a pipe system that is connected to the gas inlet pipe underneath the PMOB, which feeds the biogas into the system from 3 wells connected to the header pipe. Each well is installed 4 meters deep into the landfill surface. The gas distribution pipe is perforated along the bottom side to prevent water from entering. The pipe is designed to promote even distribution of biogas throughout the surface of the PMOB. Between the GDL and the house is a filter layer consisting of a portion of 1/4 inch gravel followed by a portion of sand. The purpose of this transition is to prevent the house material from trickling into the GDL, which would clog the material and obstruct the gas distribution. A heat trace wire has been installed above this filter layer to provide heat to the house for survival of the bugs in the colder months. The MOL consists of a 1 meter deep mixture of compost and recycled plastic pellets, as mentioned previously. This is the region where the bugs reside in, converting methane to carbon dioxide. The house is a fully monitored system containing sensors which measure temperature, water content, and the soil suction. The data obtained from these sensors aid with understanding how the system behaves in field applications. The desired temperature is based on literature that describes the optimal temperature range for the bugs to be between 25 and 35 degrees Celsius. The data collected from our monitoring equipment shows that this temperature range has been maintained well throughout the system, with temperatures in the desired range for the majority of the house depth. Water content is also a critical factor in the performance of the PMOB. While some level of moisture is important for the bugs to survive, accumulation of water at the bottom of the PMOB would impede gas migration. This is why the hydraulic behavior must be considered in the design process. Lab tests in the early project phase were used to determine the point at which the water content is too high for gas to flow through at sufficient rates. This point depends on the material that makes up the MOL. In our case, the value is about 43%. The data collected from our water content sensors show that the water content in the system is between 5 and 30%, proving that there is not water accumulating at the bottom of the system, but still enough moisture for the bugs to survive. Results obtained through the monitoring equipment are essential for the development of the design procedure. The information and understanding of the behavior through different seasons and conditions will allow us to help determine under what conditions the bugs are the most effective. This information will ultimately allow us to fine-tune the design, creating the most effective final product. Gas concentrations are monitored throughout the house over 3 different regions: the downslope, midslope, and upslope regions, where tubes are installed, allowing us to measure gas concentrations throughout the system. The system is still in the early phase. However, the results thus far have shown a decrease in methane concentrations, that the bugs are doing their job. Steps are currently being taken for the addition of air to increase oxygen concentrations in the biogas mix. This is necessary to provide a sufficient supply of oxygen to the bugs. Additionally, a method for measuring concentrations at the surface of the PMOB is in progress to determine the overall efficiency of the system. Once these additions are made and results are consistent, stress tests will be performed to evaluate the behavior of the system over sudden environmental changes, like temperature and methane loading. This will help define the design procedure. The goal of this study is to develop a design procedure in which PMOBs can be implemented in landfills across Canada. We are striving to create a better future, not only for the rest of our lives, but for the younger generation and those to come. Thank you for listening and have a great day.